Eating a town.
I didn't realize that we were on camera and being recorded, so we really have to be honest. We're now going to hear from Ed Spiegel, who's going to tell us about the phenomenology of vortices and bubbles and hot stars and disks. Thank you. Oh, and one announcement. The program is not correct about when coffee begins. Coffee will begin at 3 before the colloquium. So we will insert, following the end of this talk, some of the discussion that we would otherwise have postponed until the end of the afternoon. That way we won't have to be quite so tired at the end of the afternoon.
It's 2 minutes late.
I'm keeping track. Thank you.
Hello, everybody. It was 30 years and some months ago that I first met Oka at a meeting in Nice on convection and stars. And his message to us at that time, to the other people, to the organizers, actually I was also an organizer at that, and in the same level I was here, just I carried luggage for people from the train station and did other useful things. So Oka's message was that the people like me were just fooling around with the problem. That was the first part of it. I'm just abbreviating, if you don't mind. And the second part is the way to do it was to get on the computer and stop fooling around and solve the problem of America. Well, as you saw yesterday, he and his friends have done part 2 just as he promised. And now I'm going to prove to you that part 1 he was right about too. So that's it. Now, however, before I get on to that, I do want to take up what to me was an important issue. In 1976, which was the same year that we met at Nice, before that I was in Cambridge and I gave a lecture on photon bubbles. And Michael McIntyre, who was also at that meeting, he was the violinist in the trio, said, "What is causing this?" And I said, "Oh, it's instabilities of radiation traversing a layer." He said, "This is significant stuff. It ought to have a name." So then a big argument started in the tea room. But that night he went to his college in Cambridge and came back the next day and said he'd spoken to the classical scholars. And they said, "Oh, radiation going across something, that's photodiarrhea in Greek." So I said, "I guess that's correct, but that would be giving further ammunition to my critics, so it's very hard." I had, in fact, Prendergast and I proposed photon bubbles in the comments article, as it used to be called, still is called, I guess. But when I spoke of it at this meeting, another meeting in Nice, a previous meeting in Nice on atmospheres, I really got ripped up. I mean, Rashid's remark yesterday was like that, and it was worse. They put an insulting poem on the bulletin board the next day, and so on. So, anyway, photodiarrhea didn't fly. So I've been kind of casting about for a suitable name for the topic. Radiation hydrodynamics bothers me. First of all, radiation is a noun. I would be happy with radiator. Hydro means water, archivero. I sometimes myself put dU equals 0, but I don't feel right about it. So I've tried different things, and then came Lighthill's book called Biofluid Dynamics. And I thought, that's awful. But I went and told that to Lighthill, because we were chatting about something else. But I don't know if you knew Lighthill, but when he got through with me, I thought, oh, that's a good word after all. And so I thought I'd try it on you. And over the next months, if you think about it, tell me what you think we ought to call the subject. Now, Feynman said every body should have a problem. You just don't sort of work away. You have a problem. And here's a problem posed by Cornelius de Acher, Case de Acher, his C got lost. Although very few astronomers know of this book. I doubt that many of you know of this book, all you learned people. But it's a book called The Brightest Stars. And I don't like to read something to you if you can read. Can you read back there? Oh, Marek says no. Okay. Why is it that there are no stars brighter than a few million times the sun, hotter than approximately 100,000 degrees, then colder than a few thousand degrees? That one I think we begin to understand, because those are stars below what I call the Kumar mass. Kumar, made that estimate of the mass below which there are no nuclear burning, and that's 0.01 solar masses. And the other one, he asked about the mass of what processes occurs in stars close to these boundaries, objects that are presumably at the fringes of their stability. Now that's an amazing remark to be made in 1980, because already in 66, Ledoux had summarized the situation. That I won't read to you, just here is reminding us that he and later Hermann Schwarzschild had studied pulsational instabilities in hot stars on this cycle, and found that they become pretty violent oscillations, and it was assumed that that was the reason that they hadn't seen any stars above a mass of, 60, 70 solar masses. So, for some reason, Diache doesn't refer to that. He doesn't even refer to Eddington's limit, and that was already in a paper in 1921 in Zeitung für Physik. And in fact, if you're studying German, I recommend that paper. It's very simple German, good to start off. I guess he was just starting on it himself. And so, just in passing, that's not showing. Well, this is the nebula in Carina, and we're going to home in on that interesting looking place. There you have the so-called keyhole nebula, and there is Eta Carina, a star which is thought to be double, and someone has even said triple, but that's growing as we learn. But the interesting thing is, you close in on it, is that in 1862 it flared up, became the second brightest object in the sky. But whereas the brightest one, Sirius, is awfully close, this one is about 2,000 kiloparsecs away. And so the question is, what's going on? It's the stars in there are, I don't know exactly what the masses are, I don't think anyone does, but say in the range 80 to 100. Now, you are the cognoscenti, so you know that it's not shocking to be above the Eddington limit, but generally speaking, people do think you can't get above it. I won't bother defining this all for you. I just wanted to define here the luminosity of the star over the Eddington luminosity. That luminosity at which the radiative force on a particle supports the particle against gravity. So I call it the Eddington number because we like numbers when we do fluid dynamics, or at least I do. And however, there are other Eddington numbers, so I'm afraid there's confusion. The famous Eddington number, sometimes called N sub E, is the number of protons in the observable universe. A more amusing Eddington number, which is written with an ordinary E, not a script E, that hence this choice, refers to his skills in bicycle riding, his achievements in bicycle riding. I will not define that as a little more complicated than this thing. At least I found it so. I was taught it early by Chandrasekhar, but I always have to look it up. Anyway, what I want to talk to you about is some of the fluid dynamics that happens at or near around that kind of situation in hot objects. And one of the things that intrigued me when I was just in my first job, I went by mistake into a teaching job for my PhD, and it was murderous time because they make you work too hard. But the advantage of the place I worked in, which was Berkeley, was that there was Struve and Huang, and every day we had tea. And so that interested me in the subject. And the thing that Struve had early noticed is that apparently, I was going to say random, I don't know what that word means, but this kind of random, let me say it anyway, the random motions in the atmospheres of hot stars were even supersonic. Words like macroturbulence and microturbulence were born in those discussions. And people were wondering what caused those motions, because apparently there was no convective instability. So people refer to the instabilities of rotation. I won't dwell on that. The pulsation and instability I've already mentioned from the core. There's also the Eddington valve mechanism, but that didn't look like that at all, like, say, Cepheus. And then there's the fact that you had radiative forces, and Huang and Struve subsequently had said, they were talking about that, and they finally, in a review, and this is in one of the Kuiper volumes, that this has to do with radiation pressure, but they never said exactly how the radiative force would do this. When they were talking to me then, I started to work on this photodiuretic instability, and there were instabilities, and that didn't tell one why in the heck it got so violently turbulent. And it wasn't until 1967 when I went to a meeting in Newcastle about some geophysics meeting. There was a guy there called Mills who wanted to say that craters on the moon were caused not by impacts, but by something called fluidization, of which I've never heard. That shows the innocence of the person who studies only astronomy. And anyway, so I got to learn about that. And what fluidization is, for I doubt that there's many of you who don't know by now, when you have a bed of particles, and a fluid is forced up through that bed of particles, when the flow rate is such that the drag per particle equals the weight of a particle, the particles are levitated, the bed expands, it's like a phase transition, and you get these particles which form themselves a kind of gas and hard spheres, the dream of the kinetic theorists. So you have a two-fluid situation, and then you say the bed is fluidized. A common version of that is quicksand. Quicksand is a fluidized bed. And if you know that, you know also that if you get stuck in quicksand, just lie back and relax, because you'll float. It's trying to pull yourself out in a hurry that causes the trouble. Now, however, it's found that if the density of the rising fluid coming up through it is much less than the density of an individual particle in the bed, then you form bubbles, and this happens. And this picture has appeared in the astrophysical literature already. That was at the proceedings of that meeting in Nice, but it comes from a slim volume by Davidson and Harrison that I recommend to you, a very pleasant Cambridge volume. So that's a fluidized bed, and this bubbling, it looks like a boiling cauldron. And so if the upwelling light gas happens to be a gas of photons, the suggestion was that this is what kind of thing you'd see. And here is an elementary demonstration. This is a tube about so big, filled with these glass beads of about 10 to a millimeter in size. At the other is a windbag, a source of air. That's me, of course. I'm blowing the tube, and you see that you get this marvelous phenomenon. So what I'm really doing, and here's why this is a new trend, I am using a very crude analog computer. What is a trend backwards? Instead of these accurate computers you guys use, I have an analog computer, and it sometimes leads me astray, but it gets me thinking. In fact, there's a great tradition of that. You know, astrophysics started when people started to apply laboratory physics to stars. But in 1905, when Bénard made his famous first picture of convection in a layer heater from below, and he saw these polygonal structures, he recognized at once that they looked very like the pictures being taken of the sun by Janssen, who was working down the street in the Observatoire Paris. And so he compared these two pictures, and that was using his experiment as an analog computer too. I knew, because he's no longer with us, Bénard's photographer, and had copies of all those things that he gave me. So this is in a way a trend in which we are using not just fluid dynamical analogs, but something which is supposed to represent what radiation does, which is how Axel let me in on this meeting. Now I went the wrong way. Oh, here are some stills from that experiment you just saw. Now, here's the way it works. Where am I? Okay. You have the flow coming up through the bed. I'm not going to take time here to tell you about some of the wonderful practical applications of this process, but they're worth thinking about if you get a moment. So anyway, you fluidize the thing. Then an instability, that's in one stage, you get waves running up through that. And at that meeting, in these, where I was going to tell them about bubbles, it turns out that other people have been working on these instabilities. And the first paper, I think if you like priorities, Tony Hearn had a paper, early 70s, about this photodiuretic instability. Also, Castor was there, and he talked about it. He was anxious to stress that the instabilities are drift instabilities, convective instabilities, which is to say, if you stay in the place here, nothing happens, but if you go with the wave, it grows. That's very familiar for people studying sound waves going up through an atmosphere with decreasing density upward. So, this is a drift instability. Now, at that time, it was thought that the beds with this ratio I mentioned of the gas of the upcoming fluid being much less than the particle density, that had to be small for bubbles to form. That was the thought. And in the other case, on quicksand, there were no bubbles. And that was, to me at least, very troubling. Why should these two things give different behavior when it turned out after some considerable calculation, both are unstable. These instabilities that occur in the fluidized bed occur for all ranges of that set of parameters. Well, my student Jean-Pierre Poirier and I studied what happens when you have a pulsation like this, and that's what that is, even without the radiative pressure. We left that out, and it turns out there is a secondary bifurcation, which is a form of convection in the end. It is, I call it parametric convection, because that is what you would call a parametric instability. So, and that gives rise to these states, these bubbles, and then as the bubbling gets stronger, interesting thing happens that I won't go into very much, except to say that a big bubble, if a bubble is large, it goes faster. So the big bubbles overtake the smaller ones and merge, and they grow and grow, and that sort of thing might be relevant to things like a rapid burst of that thereby hangs another tail. And after a while, you get what's called slugging and so forth. So, all right, that's the background from which I started. One of the things that intrigued me, though, that the lab didn't have anything like the geometry we face, the spherical geometry. So here was an attempt to look at that, a wedge. This is a thing going as a two-dimensional thing almost with this side view, and this is what would be called the Healy-Shaw cell. And fluidization in those is, I'm just going to show you the wedge, gives you surprising results. This is water and sand. It shouldn't have made bubbles, but you put it in the wedge and it makes these incredible structures. And if you want to test this notion about the ratio of densities, fluidize lead shot with water, you get bubbles. That ratio is important, nevertheless. And what I think is going on is that the drift instability has big amplitude in the one case and not the other, and that's why the secondary bifurcations matter. Now, just to give you a rough idea, very rough obviously, about what a photon bubble is like, I borrow an argument from the fluidization literature. So let me say that the energy density is not the Eddington number, this is now the energy density I slipped up here. Let there be a flux fed in from the bottom, and it's driven along by the gradient of the energy density, electron scattering only, div F is therefore 0, and that you solve, of course. The way it's done in the fluidized literature, imagine someone drills a hole, a spherical hole in the medium, and you can solve the problem, and you get streamlines of the radiation field like that. So, what happens is that the radiation squeezes the bubble here and pushes it open here, and the bubble propagates. It's not a buoyancy thing in this context. So, Mitch mentioned something about buoyancy to me yesterday, but I have to have that clarified if he gets a minute. But anyway, what the bubbles really look like is that, and of course the image is that this is essentially empty, so it's optically thin, but you zip across, you hit the wall, you bounce around a few times, and out you come again. But the net flux continues upward, and the energy density here is roughly constant, as I assumed for the solution in that previous thing. So, what was interesting then, with respect to the Achel question, is that in the fluidized beds, you put a certain flow through of fluid, and everything in excess of the flow needed to fluidize the bed comes out in bubbles. So that's a way of beating the fluidization limit. Of course, it's not, this is where the minor details differ in our case and theirs, but this was something I was learning. Can you get the radiation out by some sort of escape valve? So now I switch topics, which I'll come back to this, leaving this for the moment, for reasons you'll see in a moment. And here is a remark made by my late colleague at Columbia, Lorenzo da Ponte. He has been dead a while, but he made this insightful remark, where did all those vortices come from? And we have some examples, and in effect, what it means is that almost every rotating, turbulent cosmic body that we can see it, and with enough detail, has vortices. And so, the speculation, which was driven originally, I think, by the work of von Weizsäcker, Paul von Weizsäcker died about 2 weeks ago, you may know. He was trying to explain the Titus bulb law using turbulence in the solar nebula, the turbulence in disks. And at the time, he didn't know about the vortices that we've just seen in the previous slide. But if you imagine there are such things, then you would have to say that disks have vortices in them. And by the way, that suggestion was greeted with great hoots and howls by the astronomers that I know. But this thing, by the way, was drawn for me by an artist provided by a company that hired me to write an article on turbulence for 12-year-olds in their encyclopedia. Unfortunately, she was in Chicago and I was here, so she made the picture too regular, but I decided not to bother her. My dream was, this is 79, that this would show up in the 12-year-old's encyclopedia, and 5 years later, 10 years later, kids would walk in, having noticed on the opposite page, I put a simulation that people had done in meteorology of vortices. The guy would have said, oh, look, why didn't you do the same thing here, you dummy? Look, I've done it. And bang, it's all over. But this never happened, I'm afraid. But when the suggestion was made in this astronomical literature, two important things happened. First, Marek immediately recognized that there was strong evidence from quasars for this. And secondly, Philip Yeckel said, I want to work on that. And he did, and so on. And that led to a collaboration with our friends in Turin, because astronomers were saying if you have a disk, Keplerian shear will shred a vortex, but yet here is a flow, and it's not a very high-class simulation, but it's a 2D flow in a Keplerian background. There's a Keplerian shear, and what happens is the anticyclonic vortices have a fine timing here. That is to say, the vortices turning against the flow protect themselves by this anticyclonic behavior, and this is what you see. So this is a plot of vorticity. White is high vorticity, black is no vorticity. The yellow spot in the middle of those guys are the jokers. They just threw that in to cheer me up. But by the way, this could also be done hydromagnetically. And this is, by the way, a picture of the vortice you get in the current. And it's interesting to me, and I still don't quite understand why we see flux tubes, magnetic flux tubes in the sun. but no great vortices. And of course in Jupiter we see vortices, no flux tubes. Why are they, when are they coincident? There must be a crossover which will be found in brown dwarfs. Anyway, we're trying to figure that out at the moment, gone back to this thing, this magnetic thing. Now, Giuseppe Moranti from Turin came and said, we have a 2D compressible code, what do you want us to do? I said, put a vortex, an anticyclonic vortex in and see if it's shredded. It's very happy to keep going on until the viscosity gets it. But the issue I want to talk about in this context, because vortices are now, I think, an acceptable thing to talk about in disks, is what happens to a particle in such a flow. So here's the approximate equations of position of a particle. We're in a rotating frame, angular velocity omega. We got a Coriolis force. This is the fluid flow, particle flow. There's a drag force. There's a centrifugal force in that frame, and then there's the gravity. So if we say out somewhere there's a vortex, let R be the distance from the vortex axis, let theta be the azimuthal angle around the vortex. So basically, near the vortex, this term is small. Well, I'll assume this is fairly small too. I mean, in the next picture, the whole thing is solved. I just want to give you the qualitative understanding. So when you expand around the vortex, what you're seeing is this. Factor R theta out of that, and what are you left with? Theta plus 2 omega. So if theta is the opposite side, bang, you suck in the vortex, into the vortex, the dust, and sure enough, here it goes. Now, of course you say, but how do you get turbulence in a disk? You don't have turbulence. You don't have an instability, at least one that is known. What we assumed here is that although we don't have an instability, that the disk is born in a turbulent state. So that's the vorticity field, and this is the picture you saw already, or this one. And we started out with those dust particles uniformly through the disk, and in no time, in fact, in 5 or 6 rotations, everything gets sucked into the vortices. Bingo. So now, let us go to Grenoble, where they have a tank about yay big, rotating like mad, grid oscillating on the bottom, a turbulent rotating tank. To visualize the motion, they introduced tiny hydrogen bubbles. The measurements, they claim, show that the bubbles do not affect the flow, they just mark it. Anyway, you will see, here's a side view. The bubbles go straight into the vortices, top view. So they do what particles do, even though they have negative mass. Of course, as the masses cancel out in the principal terms I showed you, which is, of course, the issue. So bubbles go into vortices. And let's say then that photons can be treated in this way. So let's assume we have a static atmosphere, barotropic, P is a function of rho, with a vortex. And so in the horizontal direction, the radial pressure gradient balances the centrifugal force. Obviously, this is integrable. This is dP over rho is dH, the enthalpy. That's integrable. There's an arbitrary function, the centrifugal potential. So I'm just going to assume that the velocity field given by that potential is what is called the potential vortex. That would be the rotation curve of a galaxy if there were no dark matter. Right? So that's close enough. So that's what it is. You don't care about that, I hope. Back to my crude version of radiative transfer. We're among friends, so I can reveal my failings. And here is what the solution of that, those transfer equations in the presence of the vortex is like. The vortices are beaming up the radiation. The radiation just slurped up into the vortex and comes out in beams. In other words, a hot star near the Eddington limit will look like the opening of a large shopping mall in rural America. If you've ever been to rural, I don't recommend it, but you know. Now, I just want to add a caveat that the motion of bubbles in fluid is rather curious. Here is an old experiment. Old, you know it's old because there was not even a camera then. Here's air. A blob of air is pushed in, and the bubble is not rotating, yet the bubble goes up in a helix. This is an astounding result, and it's still not understood, even though this experiment goes back to Leonardo da Vinci. That picture is from the Louvre. Amazing. Anyway, so here we had to settle for less. Jack Whitehead and I went to a pet shop and bought one of these things for aerating aquariums. We go to great lengths to build our analog computers, you see. And we put a porous plug here. Bubbles are coming in. The thing is rotating. One nice thing about oceanographic institutions, they got all these rotating tables. And so here we go.
Don't they have a couple of sheets of paper to put in the background?
No, that's the lab. That's the lab.
I don't want the lab.
Did you get that? No, we did. The point was we didn't expect to be showing this at a meeting. It was really fun. Because what I really wanted to do, desperately wanted to do, was to do that rotating gizmo. Oh, fine, that's even better. Okay.
82.
Oh, wow. I could tell some other stories on people. Look, what I dreamt of was a rotating fluidized bed. And just before I came to Europe, I went by way of Cambridge to come here, but the week before leaving, I was in Georgia Tech. And at a picnic, talking to this guy. It's in some ways a reward for effort. Harry Swinney was doing this fluidization in the old-fashioned way that Robert Hooke did, by shaking the bed up and down. That also fluidized it. And I said, do it by gas fluidization. It's so exciting. It turns out the guy I met was a student of Harry Swinney and inherited that remark, and he was doing gas fluidized beds. He said, can you rotate one? He looks at me like I'm crazy. He said, all right. So he pulled the motor off his lathe, turned it sideways, and the next day we were underway. Amazingly enough, and here it is, the rotating fluidized bed. And here it is. So here's the bed, fluidized. It's slowed down by a factor of 20. It's not rotating yet. It just, he doesn't have a camera on his rotating thing, you know. This was done overnight. I was trying to get people I knew, like the oceanographers, for years to do this, because it's beyond me to do things like this. And here it is. So that's the fluidized bed. The bubbling is as advertised, a little fancier with a video like this. So we're starting to speed up. Look at those bubbles bursting. Photons are pouring out, guys. Can't you just see them? No. Well, all right. At least you're not making fun.
Is that sand?
Huh?
Is that sand? Or?
That is glass beads. These guys like glass beads. I don't know why.
Because they're uniform in size.
Huh?
Is it uniform in size?
Yeah, but is that good or bad? Well, one of the spurs, as we say in the trade, that's true. And it turns out the guy who made craters that look like the lunar craters, we try to reproduce that. You have to be monodispersed. It has certain advantages. But anyway, here's one of the problems: is that this fluidized bed acts like a fluid, so the new fluid crawls up the wall, so you don't quite see what's going on in there. However, that's easily solved to stop the rotation. I wish they hadn't, but they had. And they're going to stop the rotation soon. But the thing is really going to surprise you, I hope. It surprised me when the rotation stopped. I figured just peter out. But no such luck. It was wild. Whether that would happen in the important case for us, I don't know. But by the way, this is why I told you about vortices. I think what's really going on is that in a... Wow. Surprise. In a star where the bubbles are forming, and of course all the hot stars and disks that we know are rotating rapidly, so a combination of bubbling and rotation. But in case you really wondered what happened down in that crater, we get you the top view. I insisted they do that. I couldn't see anything. Now, there's a whole literature on bubbling fluids with a great expert in Utrecht. So I'm trying to get them to let me into Holland so I can talk to them, but we'll see what happens. So here's the top. Here is not rotating yet, and it looks like my lecture will not end with a whimper, but with a bang, because this is going to have to finish me, isn't it? Yeah. Because, okay, I don't get to say the truth, but while it's running, let me tell you where I'm dreaming of. You know that to get the winds, well, let me say this. I wasn't going to tell you about this, and then I can't pull up this yet. So anyway, you know that the way winds are thought to come off hot stars is that the pumps are primed by metal lines. As the stuff starts to move away from the star, the important lines are moved, are shifted into the peak of the black body curve, and off they go. But what if you have a pop 3 star? You have no metals. How do you get a wind? Well, outside of one of those vortices now, there's an outpouring of radiation. That's what seeds. I mean, bubbles bursting can do it too, but that's what seeds. Look, there are no more small bubbles. The bubbles are starting to concentrate to the middle. But then outside one of these vortices, with radiation coming out, I'm tempted to call it, I call it a photovortex for politeness here, but I'm tempted to call it a vortex, but who knows. Anyway, it will seed the wind. Now the interesting thing in that for me is that Nader in Geneva says that when he simulates the evolution of massive stars, it doesn't agree with observation unless he puts in mass loss. But you really shouldn't have mass loss, it was said, without metal abundances. But if you do this, watch this. Is this believable or not? Now, you should criticize the various assumptions, which the differences I don't have time to go into. They're more fun than you might think, but there it is. Okay, so my time is up. Should I stop this, or?
Are we waiting for anything more in the...
No, it stopped rotating. It's now going to come back to the normal fluidized state. So
in that case,
that's it. I stopped in my end as my beginning.
Thank you very much. So now we have questions. Unless you'd like to conclude with something.
No, that's all right. Actually, never mind. I was going to do so. Oh, I'm allowed to do this anyway. What the point was, why is this? Oh, that's over there. That's the problem. Here is the Eddington number. Here I dropped the characteristic time for loss of mass. The E-folding time for loss of mass. Now, as I understand it, except for the cognoscenti in this room, people go around saying that it just, the time below the star wave at the Eddington limit or above is in fact 0. So it was supposed to be 0, I left off this part. 0, goodbye star. But, and then up you go, and I don't know what happens out here, so on. I think, in fact, the Yachar, in some sense, didn't pose the question wrong. What we want to know is a curve telling the lifetime for losing mass is a function of E. It will depend on the metal abundance, the rotation rate, and so on. This is the curve of my dreams. Because then from this, you can tell the approximate number you expect of hot stars, given that the people who make the hot stars allow us to have some, and that's the aim. Now, you can defer the bladder with some scaling arguments, but I think all that's wrong anyways. It's just as well to stop. But that's what this is about, and the talk is meant simply to tell you that there are processes here that we can begin to visualize, and the question is how to treat them so that they get this curve. That, I think, is the question to be answered.
Okay. We'll take questions.
Regarding this curve, I would have plotted 1 over tau, and then maybe it would have been even linear in the
Maybe I drew it incorrectly. Is that it? Oh, you think it's going to be linear?
I'm actually asking.
Okay, so what is the next problem I should work on?
Yeah.
Okay, you tell me tomorrow or something. Ah, Marek is with us.
It's not about the next problem. I would like only to make a short remark that Eddington luminosity is very closely related to the Eddington limit, to the Eddington number, to the Eddington number, the number of protons in the universe. And the way they are connected, Eddington luminosity, is the following. There is an upper limit for power, and it is power in Planck units, which is C to the 5th over G. It's a very big number. 10 to 54 watts. Mass independent, it's just a number. And then you may ask yourself the question, how big a mass should be that its Eddington luminosity is C to the 5th divided by G. And the answer is Eddington number times mass of the proton.
You think Eddington didn't know that?
I know that Eddington didn't know this.
How do you know that? Oh, you ask the questions, I should.
Other questions?
Am I allowed to pull this out?
Well, I don't know. I mean, can I show a little movie for Ed?
I don't see why not, because we have the discussion.
If there's 2 minutes, I think it's relevant.
Oh, yeah?
Yeah.
Okay.
Do you need time to set it up? Shall I?
As long as the projector is on.
I see.
Perhaps, may I, Ed?
Yeah, of course. Honored.
This is a movie. It's actually 6 frames taken in the singly ionized line of oxygen, the famous oxygen 2+ line, of an object known as Minkowski 29. It's a bipolar nebula, and it shows a very peculiar. Oh well, how do you get this down?
That's a good question.
Jump. I'm sorry I did that.
Oh, that's all right. We can jump.
There's a thing, actually.
Did I use your?
Yeah, of course.
Let's see. Okay. I'll put it in looping, okay, so that you can sort of see what it does. It's actually a fun thing for people into radiative transfer. I'll double the size because otherwise you won't. Oh, you don't have a pro version.
We don't have a what?
You don't have a pro version, so it doesn't really matter. Okay, here we go. What you see here is a central binary star with a bipolar nebula. Now the fun thing about this is, this spans approximately 10 years, okay, this flick. What you see is 2 beams of light basically bouncing off the side of this nebula, and it rotates, okay. It's known that the central star is a binary nebula, a binary star, and it is because of the infrared signature. It is sort of conjectured that there is a common disk around this central binary. We do not know this for a fact. Now, the reason I bring it up here is not only because it's fun for people who do radiative transfer, but I was strongly thinking about this well, basically, this is stuff that's been done by Harold Mellema, who is somewhere over yonder, and Bruce Ballack from the University of Washington in Seattle, and myself, and some other people who have, of course, done the observations. The reason I thought it was funny, because if you have this binary in a common disk, it is not at all too crazy to think that it would be a vortical hole around at least one of the stars. And that would do what you just said. Okay, the photons would just simply go up. And that would in fact explain why this lighthouse isn't really sort of going in opposite directions like what you would expect if you have an ordinary hole. You would expect the radiation to be anti-symmetric, but no such thing. It is symmetric around the nebula. So,
Well, it could just be a vortex, though.
who knows?
Yeah, but it's interesting you bring this up, because the reason I did that wedge-shaped thing is because Blanford and Rees proposed the twin exhaust model for the jets, and that means the jets were punching through an envelope. And I said, but it has to make bubbles, it's not going to make jets. I said, maybe it's geometry, so I made that thing. And it made the jets the way they said. And Rees was in New York, and I showed him that, and he said, we must have that. I'm going to take it to Cambridge and continue the experiment. Cool. And 2 years later, I found it broken in a quarter. My beautiful equipment had never been used.
They had a de Laval nozzle, I thought. So so that what made the,
But
there was
if
no rotation.
but if you bet it in an envelope, it's going to bubble, I would think, except the geometry's different. The only good thing that came out of that project is the German word for that is Doppelausgangpuffer. I think it's a very nice word. Thank you.
Any other questions?
Can I unplug? Is it just, yeah, okay.
Yes?
Do you want to elaborate on the connection between photon bubbles that you are talking about and those that Omer was talking about, who was explaining that there's possibly 2 and 3 different types of different things with the same name?
The culture is getting more complicated, but as I mentioned yesterday in the discussion, at one of the discussions, Will Sargent told me years ago, around 1980, that the student of Franz Kahn was doing convection in supermassive Fowler-Hoyle objects. But as I said, the standard fluidization bubble is not convection, not buoyant. On the other hand, if you look at what I think is going on is that you start this pulsation, standard instability, and they have the mechanism in the fluidized bed that is rather like the kappa mechanism, because the drag per particle depends on the density of particles around. So when you get that going, that starts a fluctuating gravity, and that triggers ordinary convection. You want me to stop now?
No, I wanted to ask you a question.
So that triggers convection, so that in the end, it could well be that this is a kind of convection that I call parametric convection, and that relates to the original convection. Let me stop that to ask Richard's question.
Well, what I'd like to know is, in your photon bubbles, do the grains in the fluidized bed fall through the bubble, or do they go around the bubble?
Oh, they go around. If you were to look in that book, you'd see a lovely picture of the circulant, the flow. Some of them go through, of course, but I mean the basic flow is that this bubble looks like an object going through, and the flow around looks like a Hill's spherical vortex.
So in the Gammy and Ahrens type of photon bubble, the particles go through the bubble, and the div doesn't equal 0.
And what is that a bubble?
Is that, well, it's just
A low density region.
Yeah, but what's happening is that the entropy of the gas is periodically going up and down.
Yeah, all right.
So there's a different set
that is
of,
convection.
terms.
Isn't that convection?
Yeah, that's why.
Oh, yeah, that's convection. Yeah.
Well, it's related to convection, yeah.
No, yeah, sure, but I thought it was unrelated, but now that the parametric thing looks like convection, there is a kind of family connection. I wish I had that thesis for you, but once you try to get it, Virginia Stanton Thorne is the name of the student, but it's just mixing in theory. I know it's not a word I should use.
And just to clarify a question you asked at the beginning about something I said yesterday.
Well, that's what we were talking about.
There's two classes of, two types of photon bubbles. The first one was with the magnetic fields. The first one was described by John Ahrens, and the second one was described by Gammon. And the Ahrens kind, I believe, is a destabilized internal wave, and it really is related to entropy fluctuations and buoyancy. And that has a nonlinear analog, which I'm not sure is very useful for much, but I wrote a paper about analytic solutions to that last year.
Well, you have
the other kind goes into, the other kind is a destabilized slow magnetosonic wave, and it's driven by gas pressure.
Okay.
So the Ahrens kind doesn't require any gas pressure, the Gammy kind requires gas pressure.
But they both have magnetic fields.
Yeah, that's because you have to constrain the velocities.
It's unthinkable that magnetic fields are not involved in all of this. It's just that I was coming off this analog computer, but the magnetic fields will be essential for us. But whether they're related to the origins of the bubble or are just part of its ultimate dynamics depends on details. And depends, for example, on the kinds of entropy gradients and so on. Yes.
And should be also described another kind which doesn't involve a magnetic field, which is related to boundary conditions.
Isn't this the same?
That may be most closely related.
There are instabilities of pulsation that come from boundary conditions, which is a thing that Cattaneo worked on years ago. But I don't know if that ever got anywhere. So I was in the middle of, was your question answered? I don't know.
Mm-hmm, I think so.
It was at least touched on.
Now, what is the connection, if any, between these instabilities and the discussion of a kind of Rayleigh-Taylor instability in which the lighter fluid was the radiation. Somehow your language is no longer using anything from that discussion.
Oh, Rayleigh-Taylor instability is more or less of a discontinuity. In fact, Rayleigh-Taylor instability arises in this context when, if the bubble gets too large, a Rayleigh-Taylor instability will split it into pieces. That happens in fluidized beds, but otherwise, this is in the Rayleigh-Taylor instability. You set up a thing that's a one-shot thing, and it just comes down. But in this thing, it's a continually fed instability. So it's like asking, what's the difference between Rayleigh-Taylor instability and convection? Right? If you have a density distribution, densities like that, that will give you convection. But a density distribution like that, you call that Rayleigh-Taylor, but they're just decreasing, increasing.
But if I wrote the equations down and I started with the light fluid supporting the heavy fluid,
that's unstable,
and that would be the Rayleigh-Taylor instability.
Yeah, but it's not. I've drawn my back. Forgive me. Which way is up? I'm drawing like a meteorologist, so I made a mistake. Let me plot rho, and let me plot z height. So if the heavy stuff is on top, that's convection. So, but if it's like this, that's Rayleigh-Taylor. That's the only difference. And of course, to sustain the motion here, you have conduction and viscosity. Rayleigh-Taylor, you fall down, it's all over, because you can't restore a thing like that very easily. So they're different versions of the same process, buoyancy-driven instabilities. Archimedean instabilities, perhaps they should be called. And so there's a whole range of things like that.
For example, the Rayleigh-Taylor instability tells you a characteristic fastest growing scale. Is it related to the size of the bubbles?
But the Rayleigh-Taylor thing does not give a scale unless you have viscosity, right? I mean, this thing does not give a scale. I mean, it'll be bounded by the amount of stuff here. But there's no scale except for this comes with viscosity in Rayleigh-Taylor. It's scale free, really. Just I'm not sure. All the modes are, technically speaking, if there's no viscosity, no damping, the fastest growing modes have infinite horizontal wave number because it's purely vertical motion. That's the fastest way to convert potential energy to kinetic energy. But the same is true in convection. If there's no damping from viscosity or conductivity, the growth rate in convection versus horizontal wave number is like that. And if you make a stable gradient, that's what you get for gravity waves. You know, these large wave numbers are vertical motion. Vertical motion is all you have here. So there's a thing to gravity. It's just vertical motion. That's why now if you put viscosity in, it kills this off, so you get a scale. And in fact, you put conductivity in viscosity, you can do that, huh?
Isn't there usually a sound speed?
I mean, in the laboratory case, sound is infinitely fast, so you don't worry about it. But in a compressible medium, there are two sets of modes. There's the convective modes, which are compressible but don't hear much sound, and then the sound waves, which are a whole different story. That's, by the way, another interesting issue, that the two kinds of beds, I said they're both unstable, but only one bubbles. There are two kinds of stellar atmospheres, with and without radiative forces, and both have instability in sound waves, as becoming clearer as we progress. That's a strange thing, and I've been brooding about it for a while, but I still understand how that happens physically. The equations have undoubtedly been solved correctly by now.
Well, I think we have time for more discussion, but we should end the discussion connected with the talk and then broaden the next round to all of the talks of the day. So let's thank our speaker again. So now we are free to talk about anything else that has gone on today. Reminder that this is part one of the discussion, which was previously scheduled to the end of the day. Isn't it good to get it over with now?
I'd like to make a mention of a topic for discussion, not based on my talk, but another topic.
Even better.
And that is something I alluded to yesterday, the A stars. Because may I show, oh no, let's not get back to that. But you know that one can study structures on rotating stars. But you look at the shape of the rotational broad line, and as it varies with time with the rotation, you can do a fairly good inversion and see what the structure is. And there are great large-scale motions, especially large-scale structures on the surfaces of A stars, for example. And that's thought to be inhomogeneous distributions of the anomalously highly abundant chemicals. So what's going on? So in that case, you have this picture. Here's the star. The elements are pushed up by line radiation. You get a layer of, say, mercury or manganese. You get mercury-plated stars, manganese-plated stars. It's an open question for me why they just don't leave, but that's a separate ansatz I have to throw in that they don't. And now, if you make a perturbation like that at the bottom of a layer, the radiation finds it easier to go through the thin part, so there's a kind of flow which leads to an instability like that. And finally, bang, a drop of mercury-rich stuff. So you're going to get a metallic rain. There's actually a laboratory analog called bioconvection, but pictures are put away. But that involves line transfer. And in fluid dynamics with line transfer, the forces are all in a single resonance line pushing around. That's kind of fun for the people who like to simulate line transfer. That might be an amusing problem I would mention.
So how is it different from the...
That's more like your Rayleigh Taylor, by the way.
Right. That's what I was trying to understand.
But, of course, because it's diffusive, what happens is, as this falls, it'll ablate and the stuff will then come back up. So there's a whole meteorology. So I think what we're seeing on the surface of those stars is this kind of mercury, manganese, whatever it is, meteorology. That would be sort of fun to simulate, I think, with line transfer. And it's just one line, so it's kind of nice. Thin lines, in fact.
Let's see, you mentioned POP3 stars and how to make a wind when you have no metals for resonance.
Yeah, but there are claims that that's needed.
Yes, that's the conventional wisdom. But I wondered, POP3 stars, at least in the simulations, tend to be born with very little angular momentum. So I wondered, is there some way to quantify the critical amount of angular momentum to produce the effects that you were describing?
It's not available to me as yet, but you can do, if it's bubbling, I think you'll get mass loss too. It doesn't have to be vortices, they just happen to be a more spectacular version of the situation as you saw. But bursting bubbles, you know what happens on the surface of the sea. A bubble comes from below, hits the surface, loses its air, and then collapses, and it's like a shaped charge. Squirts out a drop. Then wind comes by and you find bacteria from the sea way up in the stratosphere. And it's this sort of thing. It's a little trickier here because the photons start leaking early on. But I've estimated the bursting time of the bubbles, and for a really big hot star, it's just seconds. So you'd expect to see, if you could observe rapid variations in a star, you'd expect to see shot noise in the luminosity with timescales of seconds. So you could get mass loss without vortices. It's in fact, I was saying the vortices were there to keep the mass loss from being too large, because it lets the radiation out.
The only thing which argues for me the other way is that when I cook a pot of cream of wheat, I don't get it in my face. So
You must tell me how you do it.
well, I mean, it boils, it bubbles, but it doesn't send it off to
Right.
the ceiling.
Oh, well, but that's viscosity dominated. I mean, you know, if you do your porridge, then almost certainly the viscosity dominated. And a completely different story.
Actually, it's a pity you missed it. Did you happen to go to the Rauschenberg exhibit at the Museum of Modern Art?
No.
He had bubbling mud. It was in, he had it in the museum. And it was much like porridge, very viscous, but except it made nice noises.